Hey, folks. Okay, so before we talked about the transit method, right? How you find an exoplanet using the transits, the little eclipses. And the transit method, if you find a planet using the transit method, you can figure out that planet's radius, right? There's another way to find exoplanets, and that's by using the Doppler method, the Doppler wobble method. And that tells us something different, right? The Doppler method for finding exoplanets doesn't tell us the size of the planet the way the transit method does, but it does tell us the mass. Why? Because mass creates gravity. And so if you're watching this planet go around the star, well, the star and the planet are orbiting around each other, right? For every force, there's an equal but opposite force. The planet and the star are both pulling on each other, and that's going to make the stars and the planet orbit around their common center of mass, which is the sort of plus sign here in the middle. And so if the star and the planet are orbiting around each other, then they're going to be going in opposite directions, right? If the planet is going this way at any given instance, then the star is going to be going this way. If the planet is moving this way, then the star is going this way. If the planet's going this way, the star is going that way. If the planet's going this way, the star is going this way, right? They're both orbiting, let me check here. They're both orbiting counterclockwise, right? The planet's going around like this, so counterclockwise. How is the star moving? Also counterclockwise, right? They're both orbiting counterclockwise, but at any given instant, they've got to be moving in opposite directions. If the planet's velocity is this way, the star's velocity is going this way, which in these diagrams, we're looking at the star and the planet in the bird's eye view. But what if the Earth is down here? Right? What does that look like to us? So if Earth is down here, what can I use? What can I use to represent us on Earth? Okay. You're R2-D2. Okay. So if move this up here, right? So if that's you and you're looking at the star, now remember, all we can see is the star. Right? Yes, there's a planet, right? And that planet's gravity is dragging the star around into this wobble. But we can't see the planet. The planet's too dim. All we're seeing is the spectrum of the star. So how the spectrum shifts with the Doppler effect at any given instant depends on how the star is moving toward or away from Earth in that instant. So, in diagram A, the star is moving towards us, right, heading toward the Earth. And if the star is moving toward us at A, okay, it's moving toward the Earth. If the star is moving toward us, then its spectrum is going to be blue shifted. Okay, how about now? If you look at the star at B, the star is moving sideways. Right? It's not moving toward the Earth. It's not moving away from the Earth. It's moving to the right. It's moving sideways. Well, the star's moving, sure, because the star is always moving as it orbits the center of mass of the system. But if it's not moving toward us or away from us, then there's not going to be a Doppler shift. The Doppler effect doesn't do anything if the star is moving side to side. Only if it's moving toward or away from us. So at B, the star is moving across our view, and therefore there's no shift in the star's spectrum at the instant of B. Okay? If we go to time C, now the star is moving away from us. And so at C, the star is moving away from us, And if it's moving away from us, then its spectrum is redshifted. And then at D, now it's moving across our view again. Right? The star is moving to the left. It's not moving toward us or away from us, so there won't be a Doppler shift at all. It's moving across our view, no shift. So that's what we see. As the star wobbles around, as the star is being dragged around by the gravity of the planet, what we see on Earth is that the star's spectrum is blue shifted and then no shift, red shift, no shift, blue shift, no shift, red shift, no shift. It goes back and forth, back and forth. Based on this, which situation will result in the largest Doppler shift? Well, remember what's causing the Doppler shift. It's the velocity. We're going to see the largest Doppler shift if the star is moving faster. Is the star going to move faster if it's dragged around by a high-mass planet or a low-mass planet? Now, I said large planet and small planet. Is it the size that matters? Kind of, not really. Right? I guess I worded this a little bit tricky. Right? Because actually the planet's size is not what causes the gravity. The mass is, right? It's the mass of the planet that exerts the gravitational pull on the star, dragging it around into that wobble. So the size of the planet doesn't matter, the mass does. Now, typically, a higher mass planet is bigger, a lower mass planet is smaller. There are no examples in our solar system that violate that trend, right? A bigger planet is bigger because it's higher mass. A smaller planet is smaller because it's lower mass. So a bigger planet is going to have higher mass. If it has higher mass, it's going to exert more gravity on the star. If it's exerting more gravity on the star, if it's exerting a stronger gravitational force on the star, then the star is going to get dragged around faster. And if the star is moving toward or away from us faster, then we'll see a greater Doppler shift. In both directions. In the blue shift direction and the red shift direction. All right. What does that actually look like here on Earth? Well, what we see is that absorption line, all of the absorption lines, the entire spectrum of the star is going to wobble back and forth, right? To the red end when the star is moving away from us, and then back to the center when the star is moving across our field of view, and then to the bluer end when it's moving toward us, and then back to the middle when it's traveling across our field of view, and then back red again when it's moving away from us again. So away, toward, away, toward, away, toward, red shift, blue shift, red shift, blue shift. Right? If you look at the spectrum of a star and you see all of those absorption lines wobbling back and forth like that, then you know, aha, there's a planet there. You can figure out the mass of the planet, right? With this equation, you can figure out the mass of the planet by knowing the velocity of the star and how far away the star is from its planet, what the semi-major axis of the planet is, and also the mass of the star. So, first things first, how fast is the star moving? What is the velocity of the star? Okay, well, what you do is we got the exact same question as when we were doing the Doppler shift before, where you say, okay, the velocity of the star is the shift in the spectrum divided by the rest frame wavelength of that line times the speed of light. So, shifted from where to where? Shifted from the center out to the point where the spectrum is redshifted the most. Or you could do it in the opposite direction. You could say the shift from the center, the shift from the rest wavelength to where it is blue shifted the most. This way, that way, it'll give you the exact same velocity. It's just that if you go this way, that's when the star is moving toward us. This way, when the star is moving away from us. I say do it. I would say do the red shifted end because it makes the math a little bit easier. So, what's the easiest way to do this? Let me tell you. here on this spectrum, you can just count the number of tick marks. Like, how many tick marks is this absorption line shifted into the red? So 10 to the next big increment. So 10, 11, 12. Okay, 12 tick marks. The spectrum is shifted 12 tick marks, well, to the red, and then another 12 into the blue. We know that the scale of this spectrum is that each tick mark is 0.000001 nanometers. So what's the Doppler shift? Well, it'll be the number of nanometers per tick mark times the number of tick marks. And I'm going to have my spreadsheet do this for me. I'm going to say, okay, Doppler shift. Okay, I'm going to do this the easiest way possible. I'm just going to count tick marks. Right? Okay, the spectrum is shifted 12 tick marks. Except that one tick mark equals what? It equals 1 times 10 to the negative 6. Okay. All right. So then one tick mark is 1 times 10 to the negative 6 nanometers. So therefore, the Doppler shift in nanometers will be equal to 12 tick marks times the number of nanometers per tick mark. Okay. There's the Doppler shift in nanometers. Right? You could do the math, you could multiply those two things yourself, but I'm going to have the spreadsheet do it for me. Right? It's there to do the work I don't want to do. So what is the Doppler shift? It's 1.2 times 10 to the negative 5 nanometers. Okay. What velocity is that? Well, the rest wavelength of this line is, we're using that hydrogen absorption line with a rest wavelength of 656.3 nanometers. Nanometers. Okay. So now we've got everything we need to calculate the velocity. The velocity equals what? Equals the Doppler shift in nanometers, so that, divided by the rest wavelength in nanometers, so that. So the Doppler shift divided by the rest frame wavelength times the speed of light, and the speed of light is 3 times 10 to the 8 meters per second, so 3e8. Okay, the velocity of that star is 5.49 e plus 0. The e plus 0 doesn't mean anything in this case, so I'm just going to have it give me that. Go format cells, just give it to me as a number. 5 is a whole lot easier than 5 times 10 to the negative 0. Or, well, 5 times 10 to the 0. Okay. And it needs to be in meters. Why is the velocity in meters per second? Because we use the speed of light in meters per second. In the last micro task, we put in the speed of light in kilometers per second, and we got the velocity of the stars in kilometers per second. Whatever unit you use for the speed of light, that's the unit that you're going to get for the velocity of the star. If you want the velocity in meters per second, like we do here, then you use 3 times 10 to the 8 meters per second as the velocity. So, 5.49 meters per second. And we absolutely need the velocity in meters per second because that's how this equation is designed. This equation is designed such that you're going to put the velocity in meters per second and you're going to put the orbital distance in AU, same as always. And you're going to put the mass of the star in solar masses. And that gives us the mass of the planet in Earth masses. Okay. So we can, oh, okay. So using this, we can, well, I'm going to put in the orbital distance. I need to know the orbital distance and the star mass in order to calculate the planet mass. And the planet mass is given by this equation. So how would I program that in? Let's see here. So the planet mass equals, parentheses, the velocity squared times the semi-major axis, or the orbital distance, same thing, times the star mass, okay, close parentheses, take all of that to the 1/2 power, okay, and then multiply by 11.177. Why 11.177? Because that's the unit conversion. That's the conversion factor in order to get the mass of the planet in Earth masses. Okay, and it's saying 0 because we didn't put these numbers in yet. So, right. Okay, yep. If the mass of the star is 1.15 solar masses, and the orbital distance is 0.748 AU, and those are the units we need for this equation, then, okay, if the star is moving with this velocity and it's this much mass, and the planet is this far away, then that planet must have a mass of 56.86 Earth masses. That's a lot of Earth masses. So we're probably not looking at a planet like Earth if it has that much more mass than the Earth does. Well, how many Jupiter masses is that? Well, if there are 317... Oh, you know what? Always write down your units so you don't forget, because I'm going to convert into Jupiter masses now. Okay. So, how do I convert from Earth masses into Jupiter masses? Well, if one Jupiter mass is 317.8 Earth masses, then I take the number of Earth masses. If I take the number of Earth masses, I divide by the number of Earth masses per Jupiter mass, and that'll give me the number of Jupiter masses. This is why we convert these units, because it gives us a sense of what we're looking at. You'd say, oh, that planet has 56 times the mass of Earth, and you'd think, wow, that must be an absolutely colossal planet. But then you convert it into Jupiter masses, and you go, oh, that's a lot less massive than Jupiter. Okay, so I guess it's not the absolutely immense planet that I thought it was. It's a lot bigger than Earth, or it's a lot higher mass than Earth, but not that much mass compared to Jupiter. Well, that gives us a decent range as for what kind of planet we must be talking about. All right. Then I'm going to clean this up a little bit and make a little room. All right. So, we've studied this planet. We've discovered this planet, and we're going to study it using the transit method and the Doppler method. So what can we figure out? Well, like we did before, okay, if the transits happen on day 80, day 160, day 240, okay, then that planet has an orbital period of 80 days around the star in 80 days. Let me go back to, I've got my equations for the transit method. Okay, 80 days. 80 days is here, I'm gonna label this also. All right. the period is 0.22 years. Okay. If the mass of the star is 3.5 Earth masses, 3.50 Earth masses, sorry, solar masses. The mass of the star is 3.5 solar masses, then that planet must, we have the period, we got the mass, we can figure out the semi-major axis. That planet must be orbiting at a distance of 0.55 AU. Okay. What about this side, though? All right. If the brightness dips from 100% down to, I'm going to say there, so that looks like what, 99.966, right? Because it looks like each of these tick marks is 0.002. Yeah. So, okay, so 99.966%. All right. So then the lowest brightness is 99.966%. So that's a brightness drop of 0.034%. And if the star's radius is 2.52 solar radii, then the planet must have a radius of 5.06 Earth radii. All right, so that's 5 times the radius of Earth. Big planet compared to the Earth. So again, using the transit method, we can figure out the size of the planet and the semi-major axis. We can't figure out the mass using the transit method, though. For that, we need the Doppler method. So, the number of nanometers per tick mark, 1, 2, 3, 4, 5, 6. Okay, so the number of nanometers in a tick mark stays the same. We don't need to change that. But how many tick marks to the side does the spectrum shift? 1, 2, 3, 4, 5, 6, 7. Okay. So then the rest wavelength is 656.3 again. We're using that same, not 6 point. We're using that same hydrogen absorption line. 656.3 nanometers. What's the Doppler shift? Well, 7 tick marks means that it's 7 times 10 to the negative 6 nanometers. Guess we could have done that in our heads, but always good to have the calculator to confirm for us. Which means with this Doppler shift and this rest frame wavelength, the velocity of that star, the star must be moving at 3.20 meters per second. And we said the orbital distance, we just figured that out, right? The orbital distance is 0.55 AU, and the star has a mass of 3.5 solar masses. Now we've got everything we need to solve. This planet has a mass of 49.6 Earth masses, or 0.15 Jupiter masses. Well, 0.16. Guess best to round up there. Well, okay. Now we know a lot using these two methods, right? We got the transit method, we got the Doppler method, and now we know a lot about the star. We know what its orbital distance is. We know how big it is. We know how massive it is. What else can we figure out? Turns out a lot. So, the next step is, let's take what we know about this planet, its size, its distance, its mass, and let's do the next logical step and say, what else can we figure out about this planet? What are the other properties of the planet that we can determine from the measurements that we make using transits and Doppler wobbles. And that will take us on to the next topic. So, again, like I said last time, or before, maybe not last time, but like I said just recently, right? There's a lot of math going on here. Program it in your spreadsheet, have it do the work for us. It'll make solving these kinds of problems much easier in the long run. So, update your spreadsheet, make sure that these equations are working correctly. If you need some help with that, come on into office hours. Otherwise, onward and upward.